Hey everyone, today we will be presenting our research on the integer magic spectra of trees. My name is Dylan Obata, and I'm here with my friend Alvaro Carbonero. Both of us, along with our mentor, Dr. Ibrahim Salehi, come from the University of Nevada, Las Vegas. For our research, all graphs are simple, finite, connected, and undirected. And so to begin our discussion on the integer magic spectra of trees, we first start off by defining what an H-magic graph is. So for a positive integer h, a labeling L is defined as a mapping from the edge set of a graph to the integers mod h, excluding 0. Provided a labeling for the edges, we can also define a labeling for the vertices as a mapping from the vertex set to the integers mod h. To calculate a labeling for a single vertex, we do this by taking the sum of all of the labelings of the edges incident to that vertex and modding it by h. If we can find a labeling for the edges such that the labeling for the vertices is held constant, then we call this an H-magic graph. From here, we can define the integer magic spectrum of the graph, denoted by Im of g as the set of all integers that make the graph H-magic. And here I included a small example. If we label this edge x and take a look at the pendant vertices, that is the vertices of degree 1, and we take the sum of all of the labels of the edges incident to that vertex, we can see that this vertex labeling will be x, and likewise for this vertex. And therefore, if we let x belong to the naturals, we can see that the integer magic spectrum of this graph is going to be the set of the natural numbers. For our research questions, we encountered 3 primary ones we wanted to answer. The first one was to develop some notation that allowed us to generalize the results of previous discoveries. In particular, we wanted to separate the even diameter cases from the odd diameter cases. The second one was to find a pattern to the labelings of the vertices and edges for trees of any diameter. And then finally, we wanted a way to calculate the integer magic spectrum of an arbitrary tree. So to address the first research question, we introduced some new notation. For the sake of this presentation, we will only present the even diameter definitions. So for a tree of even diameter, di is defined as the set of all vertices distance I away from the center. Here's an example. Here we have a tree of diameter 6 with the center being marked by C. And all of the vertices highlighted in red belong to the set D2, the set of all vertices distance 2 away from the center. Moving on, we have the branch of a tree. So for a vertex U, the branch of U denoted by B of U is the set of all vertices and edges extending from U and away from the center. And here's an example of that. Here we have a tree of diameter 4, and the branch of U is highlighted in red. Finally, we take these last 2 definitions and combine them into this one. dmu is defined as the set of all vertices distance m away from the center lying on the branch of U. And for the next 2 research questions, we pass it on to Alvaro.
And with all of the definitions for trees and also for H-magic labelings, it's time to move on to magic labelings in trees. So the first thing to notice about them is that trees are very restricted. One way in which this manifests is in the labeling of the pendant edges. The pendant edges being the edges incident to pendant vertices. So the first thing we're going to learn is that every pendant edge needs to have the same labeling in an H-magic labeling. And this is easily seen because the pendant vertices will have the same labeling as the pendant edges. So for the labeling of the vertices to be constant, we need the labeling of the pendant edges to be constant too. Now, this concept of force labeling expands beyond the pendant edges. So in this figure, we are going to have the pendant vertices to the left, to the right, And so the appended edges will have the x that corresponds to them. And now notice in the top part, in the top right part, that we have to put a negative x in that edge. Why? Because we're going to have a 2x from the pendant edges, so we need a negative x for the vertex in the incident to all of these edges to come up to just x. And the same happens below. We need a negative 2x because there are free pendant edges. So we're going to have free x from them, and so we need negative 2x. So these negative x and these negative 2x were not optional. We needed negative x and negative 2x for those vertices we talked about to have the constant labeling x. But this expands even beyond that because now we're going to have from these vertices, sorry, from these edges, a negative x and a negative 2x. So we need a 4x for the vertex incident to these free vertices to have an x, because then it would be 4x minus 2x. So one question that really concerns us is calculating that number multiplying the x. In this case, for example, that 4, that negative 1, and that negative 2. We want to calculate those numbers. And we do it with this equation that we found and we defined. This definition only applies for trees of even diameter because trees of odd diameter have 2 vertices at the center. But we have an equivalent version for trees of odd diameter. It's just more complicated. So we're going to focus on trees of even diameter. As you can see, even with even diameter, this equation is really complicated. It has a sum and it has a negative 1 raised to a power. It looks really messy. But this function works. And to see it in action, we're going to go through an example. So in here, think of this as a subgraph of the tree. And on the right, we have dependent vertices. And so dependent edges have the x. Now, remember, f of e, it's supposed to be the number multiplying the x. So in this case, you should be able to guess that f of e is going to be equal to negative 1. So let's see if that works out. Once we plug in every value and we calculate and simplify everything, we find out that f of e is indeed equal to negative 1. And it is actually negative 2 plus 1, or just negative 1. And to get some intuition on why or how this function works, notice that we have 2 pendant vertices, and that's why we have a negative 2. And we have also 1 vertex that is 1 away from the pendant vertices, and that's why we have a 1. So that's why we have negative 2 plus 1, or just negative 1. For more details, you can feel free to email us at the email addresses at the end of this presentation. Now, this lemma is really nice because it basically proves that this function that we defined, that really complicated mess, it works. It proves that if we have an H-magic labeling, then the labeling that it assigns to an edge E needs to be the same as x times f of E, x being the labeling of dependent edges. So yes, f calculates the number multiplying the x. This lemma also has another implication that is maybe not easy to see at the beginning. The implication is that that the only variable is x. Every edge needs to have a really specific labeling. In particular, it has to be x times f of that edge. And again, it's really important to remark that f is only dependent on the tree. You don't need an H-magic labeling. You don't even need to be talking about H-magic labelings. F is going to calculate a number because it only considers the tree itself. Now, this implies then that x is the only variable. That's the only number we have a control over. And when choosing an x, because you cannot leave it as x, you have to choose x equal to 1, 2, or some value between 1 and h for H-magic. So when choosing an h, there are 2 problems that can arise. The first problem is what happens if f of e is equal to 0? Remember that in an H-magic labeling, an edge will have the value of x times f of e. So if f of e is equal to 0, then the labeling of that edge would be 0 too. But that's not possible because we cannot assign a 0 to an edge in an H-magic labeling. Otherwise, the solutions would be trivial. So then we have to watch out for this problem. The second problem is a little bit deeper, and we will see it more in an example, but it's basically what happens if the labeling of the center, because we're talking about trees of even diameter, so we have a single center, what happens if that center doesn't get the constant labeling too? The first problem is seen in more detail here. So as it explains in the line above, it says that if x of f of b is equal to, sorry, I think it's better if I go to the figure first. So think of this again as a subgraph of the tree where b is a pendant vertex. So then, since e1 is a pendant edge, it's going to get assigned x. But then, if you calculate f for e2, you will notice that, yes, it has to be 0. F of e2 is equal to 0. So x times f of e2 is equal to 0. But as we said before, L of e2 cannot be equal to 0. In particular, whenever a tree has a pendant path of length 2, it cannot get the constant labeling. Sorry, it cannot have an H-magic labeling. There doesn't exist. The integral magic spectrum for such a graph is always the empty set. The second problem is in here. And this problem is a little bit more complicated, but just focus on this tree. This tree is here, and we labeled every vertex, every edge according to what it's supposed to be. So f of that edge times the x. And as you can see, when it comes to the center, the labeling of the center is going to be 0. And that's a problem. Every single other vertex in this tree is going to have the labeling x, but the center. And actually, it doesn't matter what x you choose, and for any h, the labeling of the center will always be 0. So in this tree, the integral magic spectrum is also the empty set, because there is no way, no matter what x you choose, and for which h, the center will not have the constant labeling, while at the same time the other vertices having the same labeling. These two problems turn out to be really fundamental to H-magic trees. In fact, they characterize them. So a tree is H-magic if and only if there exists an integer x that solves both problems. The first one being, point 1, that no edge gets assigned the 0 labeling, and second, that the center gets assigned the constant labeling. And the second one might seem more complicated, but the left hand of the second property is the algebraic expression for the labeling that the center would get. And of course, the right is the x, so it's just saying that yes, the center also gets assigned the constant labeling. Now, this theorem might be nice and maybe it's hard to prove, but it's also ultimately a little bit evident. But a not evident question are the following. Other than by exhaustion, how can we know if such an x exists? And the second question that is even bigger is, how can we know for which h there exists such an x? The first question concerns if a tree is H-magic or not, and the second concerns an even bigger question. It's asking for every h that works. In other words, it is asking for the integral magic spectrum. Both of these questions can be solved with the next theorem that we produced. And actually, this is our main theorem. Our main theorem states that gives an expression for the integral magic spectrum of a tree. We need to consider two parts. First, C, which is the set of divisors of the elements in the range of F, and sigma, which is the labeling that the center would get minus 1. So by studying the way that the proofs of previous results, in particular those by our mentor, Dr. Salehi, we managed to find the relationship between this sigma and that set C. In particular, that relationship is stated in the main theorem. And this theorem might look complicated, but it's not really that complicated once you use it. So let's see some examples, and also to see how useful it can be. We're going to see this tree, and this tree, I know it's really complicated, right? It is pretty big. It is diameter 6, so it is not easy to understand. And as you can see, if I asked you to calculate the integral magic spectrum of this tree, it wouldn't be an easy task. It would be kind of hard. So but with this theorem, it's kind of easy. We first have to calculate f for every edge, but that's not that complicated when you do it by hand. Um, as you can see, the dividers you can do them even in your head. And after that, we just calculate the divisors of those numbers. And in here, all of the range of f was primes, 1, 2, and 3. Well, I guess 1 also included. So the divisors are going to be 1, -1, 2, -2, 3, -3, and also 0, because 0 divides every number. And then we have sigma. And sigma is, again, the labeling that the center would get -1. So it's 6 minus 8 plus 5 minus 1 equal to 1. Sorry, equal to 2. And as you can see, 2 is in C. So sigma is in C. And by the theorem that we saw before, the first case, that implies that the integral magic spectrum of this tree is the empty set. What this means is that there doesn't exist an X for every H that both guarantees that the center doesn't get, that the center gets the constant labeling, and also that no edge gets assigned the zero labeling. So both cannot happen at the same time for any H, and so the integral magic spectrum is the empty set. For more examples and for the end of the presentation, we go back to Dylan. Thank you.
For the second case, we can see that the labelings for the edges have to be x and -2x, and therefore the set C will consist of 0, ±1, and ±2. And from here, we can calculate sigma as -6 plus 7 minus 1. These numbers coming from the amount of vertices distance 2 away from the center. So in this case, 6. Plus the amount of vertices distance 1 away from the center, in this case 7, and then finally subtracting the center, so 1, and we get 0. From our theorem, we can conclude that the integer magic spectrum of this graph will be the set of natural numbers excluding 1 and 2. For a concrete example, we let h equal 5 and x equal 4. And so the pendant vertices will get labelings 4. This vertex right here will get labeling of 12 minus 8 mod 5. So that's going to be 4 as well. And likewise for this vertex. Finally, the center labeling will be 4 plus 4 plus 4 plus 4 plus 4. So 20 minus 16, which is 4. Modding that by 5 will result in 4 as well. So as we can see, the labelings for all of the vertices in the graph is going to be 4. And so this graph is 5 magic. Lastly, for our last case, we can do the same. The labelings for the edges is going to be x and -3x. Therefore, our sigma is going to be calculated to -10. And our set C is going to be 0, ±1, and ±3. And then a set of positive divisors of -10 not belonging to C are going to be 2 and 5. Therefore, from our theorem, the integer magic spectrum of this graph is going to be the multiples of 2 unioned with the multiples of 5 belonging to the set of naturals. Finally, we'd like to leave you guys with some open problems we considered. The first one being to create an algorithm that, given a set of positive integers A, see if you can construct a tree satisfying the integer magic spectrum of that tree being equal to A. The second one being given an H, can you determine exactly which X value works? Third, can you find a way to make the calculation for the range of F more efficient? And then finally, see if you can apply these techniques to graphs that are not exactly trees, but are similar, mainly the spiderweb graph. We'd like to thank Dr. Ibrahim Salehi for his contributions and support, as well as everyone else who helped us write the paper. For any questions, feel free to email us at the emails listed here. Thank you for attending our presentation, and I hope you guys all have a great day.